My name is Kylie Frew, and my project involves analyzing non-destructive image-based approaches to evaluating the mechanical properties in healing bones. Traditionally, physical tests are used to evaluate the mechanical properties of bone, which are ultimately destructive, meaning that the bone cannot be reused to perform other forms of tests such as histology on the bone. Ultimately, because multiple tests cannot be performed on the same bone, more animals must be used in the sample size to be able to accurately capture the results of work dealing with bone healing. So, as an alternative, in the lab that I work in, it has previously been developed a method that uses computational methods to measure something that we call virtual torsional rigidity within the bone. And this was originally validated on a data set that analyzed healing ovine tibiae that had small to medium osteotomies in it, which are surgical removal of sections of the bone. And these defects were 3 millimeters and 17 millimeters. The current work is now to perform an external validation of the virtual torsion test using a completely different data set that has larger defects in the tibiae. And the hypothesis is that the virtual torsional rigidity will still be strongly correlated with torsional rigidity that we receive from the physical tests performed in a lab. It is important to note that there are quite a few differences between the original dataset and the new dataset used, including the country in which it was performed, the number of sheep in the dataset, the surgical method used. The original test used plate and screws, where this one had an external fixator. The defect sizes are very different. The original had 3 and 17 millimeters, where this dataset actually had 30 millimeters, and in addition, the time frame was different. This new dataset had a longer time frame, and the type of scans used differ. So the methodology for this project first involved in receiving the in vivo imaging data from our partners. These scans were then processed in a software called Materialized Mimics to allow for the 3D reconstruction of the bone from the scans. There were a lot of artifacts in these 3D constructions due to the pins in the external fixators, so the region of interest was focused to around the actual callus segment, is the area of the bone where the osteectomy occurred and the new bone had healed, which is referred to as the callus. A finite element mesh was used using a quadratic tetrahedrons with a maximum edge length of 1 millimeter for all surfaces and volumes. After this model was created and segmented, a material assignment was used to replicate the material properties of the actual ovine tibiae bone. This is performed first by doing a calibration using a phantom, which basically allows us to understand how the pixels from the CT scans correlate to the actual density of bone. After this was calibrated using the phantom to get what we call Hounsfield units, which is that pixel intensity, we then used, which is a previously validated material model that accounts for both the soft and hard bone within the defect area. This material model assigned specific materials properties based on this piecewise function to each element in the finite element mesh. After this assignment was performed, virtual torsion tests were performed in ANSYS. This was done by fixing the distal end of the bone, which is the part of the bone farthest from the center of the body, so that it could not move at all. And then the proximal end of the bone, which is the end of the bone that is closer to the center of body, it was fixed except for a 1-degree rotation was applied. After these boundary conditions were established and the finite element simulation was ran, we calculate what I have previously mentioned as the virtual torsional rigidity, which is the sum of the moment reaction times the length of the region of bone that we're working with over that 1-degree angle of twist. And torsional rigidity just represents the amount of resistance a cross-section in an object has against torsional deformation. Before delving into the statistics of the results, it's important to note that this dataset had a large range of healers compared to the original dataset. There were what we qualitatively classified as good and poor healers, where the good healers had a very thick, strongly developed callus where you can't really see through the center of the bone, as compared to the poor healers where there is not a consistent set of connections between the proximal and distal ends of the bone. Now, when comparing the results of the virtual test to the physical test, we can see that there is a high and strong correlation between these tests based on the Pearson's correlation of 0.673, and it is statistically significant with a p-value of less than 0.001. Additionally, a t-test was performed to see if there was a difference between means, and we determined that there was no significant difference between means with a p-value of 0.350. After that, the standard way of determining if the virtual torsion test is a viable substitute for the physical test is by comparing the root mean squared error between virtual torsional rigidity and the physical torsional rigidity represented by the letters GJ to the standard deviation of the biomechanical or physical data set. Since the root square mean error is less than one standard deviation of the physical test data, we can conclude that virtual tests using computational methods were a viable surrogate for the physical tests, allowing for researchers to use virtual methods in lieu of the physical destructive methods and be able to expand upon the data they could receive from their data set. And since this was an external validation, it just shows that this test can be used across a wide set of data sets because the original and current data set differed in both surgical techniques, sample types, and other experimental characteristics. So this work is ultimately exciting because it allows for researchers to maximize the amount of data they can receive from their data sets and reduce the amount of animals needed to be used in these data sets when testing for methods to accelerate bone healing. Thank you.